Hey guys, today I'm going to take you through the first lesson of our lines and planes unit, and we're going to talk about equations of lines in 2-space and 3-space. So equations of lines in 2-space, we're actually familiar back from grade 9 with two types, and they are slope y-intercept form, or y equals mx plus b, and the standard form of a line, which is just found by rearranging slope y-intercept form. In vectors, we call this the scalar equation of the plane. We can also use Cartesian vectors to set up what we call the vector equation of a plane, and the parametric and symmetric equations of a plane can simply be obtained from the vector equation. So we're going to go through a couple examples where we kind of solve for some of these so that you can see the connection between all of them. So first I want to talk about vector equation of a line in 2-space. And basically the job of this vector equation is to represent all possible points xy on the line, similar to how our slope y-intercept form and standard form have a general xy in them to represent all possible xy coordinates that could be on those lines. So we want our vector equation to do the same thing. And it's going to basically do this by describing the resultant vectors that start on the origin and end on a point on the line. And in order to create this vector, we need two things. We need a position vector out to some point that we know is on the line for sure, and a direction vector which will be parallel to the line. So essentially this direction vector is kind of like our slope, and our position vector is kind of like it could be like the y-intercept in y equals mx plus b, or it could be any other point that we solve for on the line, or that we know is on the line, I should say. So as a summary here, or as a visual here, you can actually see that if I have a position vector and I add this with some scalar multiple of our direction vector, I'll actually get a resultant out here, which will go to any point on the line. Now, if the reason for this scalar is that we can actually scale our direction vector up and down, and that will result in another resultant vector, which will go out to another point on the line. So you can see how this generates multiple infinite different resultant vectors, which will go to all of our infinite different points on our line here. Okay, so in summary here, we have our R0 vector, which is the position vector to any point on the line. We have our resultant vector, xy, which basically represents all the infinite points that are on the line. And we have m, our direction vector. And then we also have a scalar multiple t, which represents all possible scalar multiples of the direction vector, which helps us generate all of those different xy coordinates. And t is going to be from the set of real numbers. Okay, and then from this vector equation, as I said above, we can use this to get the parametric and symmetric equations as well. So let's take a look at an example. So we're going to start with something like a classic question that we had in grade 9, which is, let's just find the slope y-intercept form of the line on this graph over here. Okay, and then I also want to rearrange this into standard form as well. So in order to find y equals mx plus b, we need to plug in the m and we need to plug in the b. The b is the y-intercept, so this is simply just going to be 3. And our m, we can find in a couple different ways. If I have 2 points, I can do delta y over delta x, which is basically just y2 minus y1 over x2 minus x1. Or we also know that slope, or m, represents rise over run. So if I choose, let's say, the closest next coordinate here, I will go down 1 and right 2 to get there, which means that my rise is -1 and my run is +2. So I think that's probably the easier way, just use rise over run if you have an actual graph that you're going from. If you have 2 points, then you're going to use this guy up here. Oops, you're going to use this guy. Okay, so if we rearrange to get this into scalar form, or I guess I should say standard form for now, basically what we want to do is just move everything to the left side and have the right side set equal to 0. We also ideally do not want to have fractions in here, so we're going to multiply through by the denominator of any fractions just to make sure that we have everything in a standard format. That's why this is called standard form. And we'll typically also try to make sure that the coefficient of x is positive. So when we do this, we'll move x over, we'll get positive half plus y minus 3. Coefficient of x is positive, which is good, but we do want to come through and multiply every term by 2 to eliminate that denominator of 2 in front of the x here. So we're going to get 1x plus 2y minus 6 equals 0 for our standard form. All right, now when we go to find the vector equation here, I want a direction vector which will be parallel to my line. So I can actually use this direction vector that starts at 0, 0. Wasn't a very straight line. Starts at 0, 0 and goes out to this point here. That's essentially this little vector that I use to find rise over run. So you'll notice that the rise here is -1 and the run here is 2. So that's going to be our direction vector. And I also need a position vector. So you can actually choose any point on this line here, and you can draw a vector going from 0, 0 out to that point on the line. So let's say we already have 3 marked off here as the y-intercept. So let's say we could choose maybe this as our position vector, r0. So what are the coordinates of each of these vectors? Well, if they start at 0, 0 and go out to a point, that means that our r0 vector is going to simply be 0, 3. And our direction vector is going out to the point 2, -1. So that's going to be our direction vector. So when we set up our vector equation, you can use r as resultant, or you can use, sometimes we say xy. And then we're going to say the position vector plus any scalar multiple of our direction vector, which lets us generate all possible xy coordinates on the line. Okay, so essentially what we're saying is that if we take this direction vector and we multiply it by a scalar multiple, I'm going to get all sorts of different resultants here. I can get this resultant, or if I multiply the scalar, let's say here, then I can get this resultant vector, and that will generate the 0.41 on the line, and so on. So all the different possible resultant vectors that we can get. Okay, it's also important to know that the vector equation of a line is not unique, which means that although we do want to make sure that we have the same direction vector, there are infinite different position vectors that we can actually generate on this line because there's infinite points. So if you chose a different point, let's say maybe you chose the y-intercept, which is 6, 0. That could have also been a position vector as well. So another option could have been xy equals 6, 0 plus t times the vector 2, -1. Many other options here as well. If you chose, let's say, this point out here, -2, 4, that could have also been a position vector that you use as well. So lots of different options for that position vector. Okay, it doesn't have to be an x or a y-intercept either. Okay, so I'm just going to work off this guy, just so that we kind of all are figuring out the same thing here. So let's look at finding the parametric equation. So basically what I want to do for parametric is I want to separate the x pieces out into one equation, which will basically be x equals 0 plus 2 times t. And then we're going to take a look at separating out the y components as well. So y should be equal to 3 and -1 times t. Sorry, I just realized that I kind of erased there. So y equals 3 minus 1t. So when you look at this, you should actually see the position vector here and the direction vector here. So of course we don't usually write -1, so you have to remember that the coefficient there is -1. Okay, and then we will definitely as well just simplify. We don't need this 0 in here, so we can just say 2t. Okay, so this will be our solution for our parametric equations. And then from those, we can find our symmetric equations by simply isolating for the parameter. The parameter is t. So if I have x equals 2t, if I isolate for t here, that becomes x over 2. And if I have y equals 3 minus t, if I simply swap the t and the y here, I'll get t equals 3 minus y. And what you're going to do here is, now that you have the t's isolated, t needs to be equal in both scenarios because they both basically come from this same t up here. So I know that x over 2 must be equal to 3 minus y, and that will be our symmetric equation. Okay, and lastly, I want to see if we can find the scalar equation given our new vector equation and parametric and symmetric equation knowledge. So we did find it up here, so we should expect our answer to be x plus 2y minus 6 equals 0. But I'm going to show you how to get that from the vector equation, and if you happen to have the symmetric equations, you can get the scalar equation really quickly from that as well. So our first option is if we have the scalar equation, we can, or sorry, the symmetric equation, we can use that. And right now our symmetric equation is x over 2 equals 3 minus y. So the goal is we need it in this format here. So we're going to move everything over to one side. So move the y over, move the 3 over, and now you're probably noticing that this is pretty similar to what we had here, and we're simply going to multiply through by 2 just as we did above to eliminate any fractions. So multiply this guy by 2, then we'll get x plus 2y minus 6 equals 0. So there's option 1, if you happen to have gone that far to find symmetric equations. Our second option, I'm going to show you how to get the symmetric equation directly from the vector equation. So right now our vector equation is 0, 3 plus t times the vector 2, negative 1. Now what we need, and what it says above here, is that we need some vector AB that's going to be normal to our line, and what that means is it needs to be perpendicular. So if you remember back from unit 1, I taught you a little trick to find a normal vector or a perpendicular vector. And in order to find the normal vector, that means that we actually have to use the direction vector and find a vector that's perpendicular to that. So my normal vector, if I take these two coordinates and swap and then change one of their signs, then it should dot with the direction vector to give me 0. So I'm going to swap them, and then you need to choose one sign to change. Typically, if we can, we'll try to keep things positive. So I've swapped both of them, and then I made the negative 1 positive 1. Now you can check this if you're not 100% sure by dotting them and seeing if you get the dot product equal to 0. That should tell you that they are in fact perpendicular. All right, so that's our normal vector 1, 2. That's going to be the a and b in my scalar equation here. So the question is now, how do we find the c in this? Well, that's where the second part of our vector equation comes in handy. This is a position vector that goes out to a point on the line. So we're going to plug in the point 0, 3. So plugging in 0, 3 here, we're going to solve for c. And a lot of my students, they forget, they try to kind of like do this quickly in their head, and they forget that this value, once you simplify the first two pieces here, actually has to be moved to the other side. So sometimes they'll get the positive version or the negative version of c, which will be the wrong version. So just be mindful about that as you're solving, that actually has to be moved to the other side to isolate for c. Okay, and as you can see, we got the same equation that we got using option 1. Let's take a look at another example here. So we're going to consider the line. These are the parametric equations of the line, and we're going to use those to find the coordinates of 2 points on the line. So you can find any point on the line by simply choosing a value for your parameter t. So let's say we choose t equals 1. This is going to generate a point x using the first one, and its y coordinate using the second parametric equation here, and that will generate a point on the line 5, -1. So here's a point on the line, and you can choose really anything for t. Let's say maybe we choose -2 for t, as long as you make sure that you plug in the same thing into each of those to get your point. Okay, I can also do this in vector format as well by simply choosing a parameter t and then multiplying that by the direction vector and adding the direction vector and position vector. So this is essentially kind of like the same thing, but we're just separating it out into x and y. So here we're getting 7, and down here we're getting -13. So that generates another point on our line, 7, -13. Write a vector equation of the line. So let's say we use this point, and I actually already can see the direction vector kind of buried within my parametric equations here, and it is 2, 4. So when we create our vector equation, you can say r or xy. I'm going to do the position vector out to 5, -1, added with the parameter t, 2, 4. Or alternatively, if you want to use the point that's given to you with the parametric equation here, you can use 3, 5. So it doesn't really matter. I could have also used the other one that was given to me, which is the other one that was found, not given to me, which is 7, -13. So infinite answers for that piece of the equation. Okay, but we'll just work off the parametric equations that we were given here. So I'm going to use 3, -5. So there's our vector equation. And we're going to use that vector equation to write the scalar equation. So if we have our vector equation, then we're going to find a normal by using our direction vector. So we're going to swap the coordinates, and we're going to change the sign of one of them. So typically I'll try to keep the x coordinate positive, and so I'm going to make the y coordinate positive here. If you did make the x coordinate negative, you're simply just going to take your scalar equation and multiply through by a negative at the end, or divide out a negative, I guess we could say. Okay, so here's what we have so far. In ax plus by plus c equals 0, we have a and b as 4 and -2. And then you can use any one of the points above, so you can use 3, -5, 5, -1, 7, -13, or any other point that you may have found to plug in for x, y. I'm going to use the one that was given to us just in case we made a mistake above. That way it won't affect my answer. Okay, and just remember here, if I get 10 plus 12, I have to actually move that to the other side. I'll get -22 for C. And what we do so that all of our equations are standard and the same is if I have a multiple that's in front, so you'll notice that each of these is a multiple of 2, and I can common factor 2, we're simply just going to divide that out from each term. And if the first term was negative, I would divide out a -2. And that just allows us to all make sure that we have the same equation in the end. That's why it's called standard form, right? We all want one equation that can express this the same, and it should be the same no matter what position vector you chose. And we're going to determine if the line from part A is parallel to line 2. So the line from part A has direction vector. We'll say direction vector from line 1 of 2, 4. And the direction vector from line 2, we can see here, is 3, 12. And in order for these to be parallel, the direction vectors need to be collinear. And we did a little test for collinear vectors back in our first unit. And basically, I just want to know, excuse me, if 2, 4 is some scalar multiple of 3, 12. So the way that we can kind of solve for this is just separate out your x coordinates with the k and your y coordinates with the k, into kind of two separate equations and solve for k. So for the first one, 2k equals 3 would mean that k is equal to 3 over 2. Now, if these are collinear, if I set up the same equation with the y's, they should have the same scalar multiple. So if I divide out 4 here, we'll see that k is actually equal to 3. So because these guys are not equal, that actually tells us that these lines are not parallel. If they were equal, we would say the lines are parallel. So a line in 3 space can also be defined by vector, parametric, and symmetric equations, but we can't define a line in 3 space with a scalar equation. Actually, in 3 space, a scalar equation defines a plane. Because a plane is a two-dimensional flat surface that extends infinitely in both directions. Imagine like a line in 3 space that's basically just widened to extend in all directions. So the scalar equation in 3 space actually represents that flat surface. So we can use our 2 space equations and simply we're adding on a z component to the vector equation, and then that means that there will be a third parametric equation to represent the z component and a third piece of the symmetric equations as well. Okay, so let's just take a look at an example in 3 space. This time we're going to be just given 2 points on the line, and we can find a direction vector by simply using those 2 points on the line, and this kind of allows us to find like the slope of the line in a sense. So I'm going to use these 2 points and I'm going to find my direction vector as AB here. Okay, so remember when we do AB, we're going to do tip components minus tail components. So B components minus A components to find that direction vector. And that should give us the direction vector 1, 7, -9. And if you're given 2 points, you can actually use either of these 2 points as your position vector. So our R0 vector or position vector is essentially just going to be the vector that goes from 0, 0, 0 out to point A. So that's just going to be the vector 2, -1, 5. Or you can use OB as your position vector as well. So when we do our resulting vector equation here, you can say R as resultant vector or X, Y, Z is equal to the position vector plus our scalar parameter there times the direction vector. So this is one option. You could have also used the position vector 3, 6, -4 if you wanted to. Okay, and we're going to use that vector equation to create parametric and symmetric equations for our line. So very similar to how we did this in 2 space, we're basically just going to take the x components, the y components, and the z components and separate these out into their own equations. So we'll have 2 plus 1t for x, y equals -1 plus 7t for y, and z equals 5 minus 9t. Okay, and then rearranging each of these in order to find your symmetric equations. Basically just want to get t by itself. So in order to do that, we'll move the 2 over here and we'll get x minus 2. For y, we're going to move the -1 over. We'll get +1, and then you need to divide out the 7. And for this guy, I think what we'll do is we'll switch z and t. Usually like to have t positive, and then we'll divide out 9. So we'll get t equals 5 minus z over 9. And then in order to complete the symmetric equation, we're just going to set each 3 of these equal to one another, because they're all equal to t, so they all must be equal to one another in this format. So there's our symmetric equation, and these would be our parametric equations. Okay, and finally, we're going to determine if the point C lies on the line. So there's a couple ways that we can do this. We can use our parametric equations, sub in x, y, and z, and isolate for the t. And the goal here would be is if the point lies on the line, then the t for all of these is going to be equal. Or we can use the symmetric equation and plug in x, y, and z, and just simply see if we get 3 equal values. So I'll show you both here. So using the parametric, we're going to plug in 0 for x. So that means 0 equals t, 2 plus t. And that means that t equals -2. And then we're going to plug in -15 for y. And isolate, so bringing the 1 over, we get -14. And that means t equals -2. So far so good. We just have to check the z. So moving the 5 over, we'll get 4. And this is going to give us -4/9. Now this is not equal to 2, so we need to have a 3-way match here in order for the point to lie on the line. So therefore, C does not lie on the line. Okay, and if we were to use symmetric instead, essentially the symmetric is just derived from the parametric equation, so we should get something sort of similar when we do this. I'm just going to plug in 0 for x, and then -15 for y. This is +15/7, and 9 for z, which is 5 minus 9/9. So what you'll notice here is we actually kind of get these, because these are all equal to t, we'll actually get these same values. And we see that these are not equal. So therefore we would say C does not lie on the line. Okay, we don't need to write it again, we have it above. But that's how you can use kind of either one to solve to see if your point is on the line. We can also actually use the vector equation as well by simply subbing in 0, -15, 9 in for x, y, in for x, y, and z here, and then we'll simply move the position vector over, and we can see if these are scalar multiples of one another once we've done that. So that's another option as well.